And so it's my very great privilege, first of all, to introduce the recipient of bring the recipient of the David Craig Medal up to the podium. And I will present his medal after I've read this brief citation, or the citation will be read by Professor Jagadish. But want especially to remember the late Professor David Craig, who of course was a previous president, and whose outstanding contributions to chemistry as an Academy Fellow is recognized by the contribution of a high order to any branch of chemistry in the David Craig Medal. The recipient of the 2016 David Craig Medal is our Academy Fellow, Professor Jeff Reimers, and Jeff is here, and I want to present you with the medal and congratulate you, Jeff.
Professor Reimers pioneered the application of the chemical quantum theory of coupled electronic and nuclear motions to large systems of biochemical and technological relevance. His work explains how, during photosynthesis, the protein structure manipulates the complex light-matter interaction around the special pair solar to electrical conversion apparatus to control energy harvesting. He has also developed ways of interpreting the chemical signatures manifested when single organic molecules conduct electricity, and he has evaluated the role of chemical quantum effects in manifesting consciousness. Professor Reimers, my congratulations. Now I invite you to address the meeting on when chemistry becomes quantum, applying David Craig's principles to modern nanotechnology and biotechnology.
Thank you very much. It's a great honor to receive the David Craig Medal. Trying to look at my work over my career, I've worked with many famous people like Professor Hush and Max Crosley, who are here in the audience today, but my work has really been to combine the works of David Craig and Professor Hush and others, and then to advance them into new fields. And I'd like to thank NCI, who provided all the computer time for everything we've done, the Australian Research Council that funded me as a fellow for 25 years, and UTS and Shanghai University, who have given me the opportunity now to apply these ideas into molecular biology. David Craig unfortunately died last year, but he was a great inspiration to all of Australian science. His PhD was on conjugated and aromatic molecules, looking towards things like graphene, done in the 1940s. And he coined the much-loved expression, must be 100,000 papers a year, which use it ab initio. And this came about in the first of the two papers here. I've looked at Craig's papers, many influenced my life, but in particular these two. The first one includes Ian Ross, a very famous fellow of the Academy of Science here, and talks about configuration interaction or electron correlation. And again, there are hundreds of thousands of papers each year nowadays which discuss that, but Craig was the first ever treatment of electron correlation with Ian Ross. The second paper looks at the spectrum of benzene. That's the interaction of the vibrations of the benzene molecule with the electronic motions inside the benzene molecule, a mixed quantum effect. And that really strongly influenced my life. My first paper, 31 years after that one, was on exactly the same system as Craig had worked on, and we just fixed up a couple of the really minor details. But that was done with my honours supervisors, Ian Ross and Gad Fisher, who were two of Craig's students. For me, Craig solved benzene. For me, the challenge was chlorophyll. And people applied Craig's ideas to chlorophyll in 1962 and found the problem to be quite difficult. And for me, there was a quest from 1989 when I first ran into the issue until 2013 when we finally solved it, to understand the spectrum of chlorophyll, arguably the world's most important chromophore. Without understanding how chlorophyll absorbs light, you can't understand how photosynthesis works. And yet, there was this fundamental problem that had never been worked out. The problem sort of runs like this. This is the, in blue here is the red here and orange here absorption spectrum of chlorophyll. And it has one large peak which everyone knows the origin of. It's called the QY electronic state. So QY means how the electrons move when the light interacts with the molecule. But QY should have one small sideband, but here there are two. There's one too many. So there must be a different electronic motion that's being excited by the light at the same time, and that will affect photosynthesis. And to get a better idea of it, down the bottom here is magnetic circular dichroism spectroscopy. For the Y band, that's identical to the absorption, but for the X band, it gives a negative sign. And there are two peaks here with a negative sign. One of them must be QX, so the question is which one? And in 1962, using Craig's ideas, the assignment was made to the big band. But in 1982, that was changed to the smaller band, and there were decades of evidence supporting the smaller band. And after I'd worked on it for decades without any resolution, I got together in 2012 with Avi Freeberg and with Elmer's, oops, what have I done? And with Elmer's Krauss. So they were the world's two leading experimentalists on the topic doing new experiments. And Avi Freeberg in 2009 published a paper saying it was this band, and Elmer's Krauss from ANU here in 2010 said it was this one. So the debate continued 50 years later. So I got together with them and also with Rika Kobayashi from NCI, a sponsor of this meeting, and she programmed new quantum chemistry electronic structure methods that are now extremely widely deployed across the world, looking at anything to do with moving electrons or moving light through molecular systems and nanotechnology. And she put this together to work on the project. And the answer was, it's not one or the other, it's both. The idea that it's one or the other is a classical idea. Chemistry is usually treated in with classical ideas for the nuclear motion. But it doesn't have to be, as Craig pointed out, and what you actually have is a quantum superposition of the two classical states. Both are the electronic transition at the same time, a very rare phenomena and yet critical to the operation of photosynthesis. Amazing, really. I've worked on other things that directly relate to Craig's work as well. So Craig published the first paper on electron correlation, and an example of electron correlation is the van der Waals force. And that holds biology together and controls self-assembly. So we're getting here at really the fundamentals of a lot of modern nanotechnology and biotechnology. So with Max Crosley at Sydney University, I have many papers with he and Professor Hush. Max made these molecules, they're porphyrins with long chains. Professor Hush's interest was in molecular electronics to see how you could make devices out of these molecules. But we put them on graphite surfaces and they self-assemble. The advantage being we can get accurate data from both calculations and experiment. Also important to this was my PhD supervisor, Bob Watts, and I learnt many techniques from him. And so here we're combining Craig's, Hush's and Watts's techniques with the molecules of Crosley to, for the first time, get an idea on the thermodynamics of self-assembly. So using a scanning tunneling microscope, we measured images of 3 different porphyrins with different lengths, 11, 12 and 13. And these are what we find. The structures look like this. A single molecule can have a completely different looking structure called a polymorph. Just by changing the chain length by 1. And so can we understand that? And the answer after we've done these simulations is, this is one polymorph here. So here is solvated surface and solvated molecules. You have to, the molecule's in solution, you have to take the solvent off it and take the solvent off the surface to make the self-assembled monolayer. And that costs 110 kilocalories in energy. Huge penalty to desolvate it. Then entropy doesn't like forming a monolayer. That's a 40 kilocal penalty. And then Craig's term, the electron correlation term, brings you down here 150 kilocalories. This is the net free energy change, almost nothing. Here's the experimental value. We developed the experimental technique necessary to measure that value, as well as the computational methods needed to calculate it. So we're solving the equations of motion of every electron in the system, and we're ending up with the free energy of forming the self-assembled monolayer. A different self-assembled monolayer polymorph, completely different balance between these three fundamental forces, and yet we can see what they are and see how they control self-assembly. And lastly, the van der Waals force has always been known to be due to electron correlation, but now we're looking at a different problem for which is also dominated by electron correlation, but no one ever expected it. And this is a gold nanoparticle, extremely widely used in nanotechnology, held together here by sulfur-gold-sulfur bonds holding organic molecules to the surface. And people always believed that they were chemical bonds called gold-1 thiolates, but no one could understand the synthetic mechanisms for making these. There were many syntheses, but the mechanisms were unknown, why some worked and others didn't. No one really knew. But we showed that the bonding is not gold-1 thiolates, it's the dispersion force, the van der Waals force again, very strong, but it holds it together. You can make the gold-1 thiolate, but it will destroy the nanoparticle, it will destroy a surface, it will not stabilize it. So understanding this, we could predict what the mechanism of the reaction had to be, and then we did the experiments and measured the intermediates that were there. So using Craig's ideas, we've really understood from first principles how to make these nanoparticles. And finally, I'd like to say that this work would not have been possible without my high school teacher from 1969 to 1974, Tony Gutierrez. He's in the audience somewhere. I'm going to stand up there, Tony, and his wife Annette. And it's due to the teaching of science in schools throughout Australia that makes the sort of research we're seeing here today possible. So I'd particularly like to thank them and all science teachers in the country, and thank you all.
Thank you, Jeff, for a beautiful talk. Are there any questions or comments? So maybe I'll pick up on your last point about the gold nanoparticles. Is sulfur necessary to stabilize the gold nanoparticles, or can you stabilize them without sulfur?
There are many things that can be used. The rage at the moment is carbon compounds. So gold is a carbon analog. It can form single, double, and triple bonds, just like carbon can. So sulfur was believed to be unique on the periodic table, and that its bonding was completely different to every other element. We've shown that this is not the case. Nitrogen can also be used, forms almost identical bonds for the same reason, the van der Waals force, whereas if you thought it was a chemical model, then you'd expect something completely different. So we can also do selenium and tellurium and pretty much every other type of bond. Gold is a metal, but it has the same electronegativity as sulfur, and gold can oxidize every metal on the periodic table. And these ideas were not taken into account. The gold as a noble metal was not taken into account for 30 years of chemical theory on how nanoparticles form.
Any further questions or comments? If not, could you please join me to thank Jeff for a beautiful talk?
Thank you.